Hi everyone, in this video we are going to show that property of symmetric group. That is, the inverse element of an n cycle 1, 2 to n is an n cycle again, n minus 1 to 2, 1. Okay, to proceed with this proof, we begin with n equals to 2. That is, 1, 2, the inverse element of 1, 2 should be equal to 2, 1, but 2, 1 is equal to 1, 2 again. We don't know if this is true, but to prove, we have to prove 1, 2 composition 1, 2 is equal to identity element in symmetric group. And this is a true property, because on the right we have 1 going to 2 and 2 going to 1, and on the left we have 1 going to 2 and 2 going to 1 again. But if we look to composition, 1 goes to 2 and 2 goes to 1. Here 2 goes to 1 and 1 goes to 2. Of course, this is the identity element, so this is correct. But we know that in general group theory, if we have two elements A and B and the product of them is equal to identity element, then B is equal to inverse of A. Therefore, we showed that 1, 2 is equal to the inverse of 1, 2, but 1, 2 is equal to 2, 1. This is exactly our property. Now we have to proceed with the induction step. First, use the property. If we have A and B, two elements in a group G, then the inverse element of the product is the product of the inverses, B and A. Okay, the second property belongs to the symmetric group. Look, if we have 1 to n cycle and we have a composition with n to n plus 1, what is the result of this composition? On the right, we have n going to n plus 1 and n plus 1 going to n. But on the left, n goes to 1. So we have n plus 1 going to 1. And again, on the left, n plus 1 going to n plus 1, because n plus 1 doesn't belong to the cycle. So the result is clearly 1, 2, 2, n plus 1. Okay, now we prove the induction step. We begin writing the n plus 1 cycle, okay? The inverse element. But by the second rule, or the second property, we can change and write 1 to n product n plus 1. Of course, the inverse of this product. But by the first property, we know this is n plus 1 minus 1 product 1, 2 to n minus 1. Now, by the induction, we know this form, n minus 1, 2 to 1. Okay, so we write that guy in this form, n minus 1, 2, 1. Okay, but on the left, this is a 2 cycle and the inverse of 2 cycle, but we have already seen this is n plus 1. If you want to write more precisely, write n plus 1, n, and the composition, n minus 1 to 1. Now we have just to check that this composition is equal to n plus 1, n to 1. Look, on the right element, 1 goes to n, and n plus 1 goes to n plus 1. But on the left element, n plus 1 goes to n, and n goes to n plus 1. Then the composition is, of course, 1 going to n plus 1, and n plus 1 going to n. Okay? And then we finished our proof.